So colligative properties, it sounds complicated. There's a little math to it, but it's not bad. Okay, so don't let it get kind of bogged you down, scare or anything. What I'm going to do is I'm going to end up explaining to you why we put salt on the roads. Okay, essentially, like why does that work? So we're going to talk about that today. And it comes down to something called colligative properties. So these colligative properties are properties of solutions that are affected by the number of particles, but not the identity of what they are. So it wouldn't matter if it was like sodium chloride that they're putting on the streets or potassium chloride, or, they could put anything on there. It's going to have the same effect. Okay. So that's what they're saying by the identity. The number of particles here in your math that we're going to get to, we're going to represent with a little I. Okay. It's called the Van Hoff factor, I believe. Don't worry about that. I think of it as the interference factor. Okay. So the more things you have, for example, magnesium chloride versus sodium chloride. Okay. Here, when this gets in water, it's going to break apart into how many pieces? 1, 2, 3. So this interference factor would be 3. How many pieces would this break up into? 2, a sodium and a chlorine. Okay. If we had scandium, okay, if we had scandium chloride, it would break apart into how many pieces? 4. So you get the idea? Okay. Now these are ionic compounds. This is a metal and a non-metal. When we're dealing with a molecular solid, like they will also put beet juice. Have you ever heard of them putting beet juice on the roads in the winter? Okay. They will do that. That is going to stay, that has sugar in it. So we're just going to say that that's glucose. This is a molecular solid. It's not going to break apart into multiple pieces. Okay. So its interference factor would be 1 because it's going to stay together. These are all non-metals. Okay. That's how you can tell that this is going to stay together. These are metals and a non-metal. Metal, non-metal, metal, non-metal. This is ionic bonding. So it's going to break apart into its particles. All right. So I call that an interference factor. Right? So these ionic compounds are electrolytes. They're going to disassociate into water. They're going to enable it to conduct electricity. Sometimes there's strong or weak electrolytes. We did a lab earlier this year that I gave you data about things being electrolytes. Remember that ionic compounds are going to become electrolytes. Molecular solids, then, they'll dissolve, but they're not going to conduct electricity because they don't have those charges. So when this goes into water, it's going to stay as one piece. Okay. When this goes into water, it's going to break apart into a sodium ion and a chlorine ion. And because these are charged, that will allow these to actually conduct electricity. Okay. All right. So these different colligative properties, then you're going to have vapor pressure lowering. So we talked about how you would have a sealed container, and if you had a liquid in there that is now a solution, less of that will go up into a vapor causing pressure than if you had a pure substance down here. Okay? It's going to interfere with how much goes up into the vapor form. You're going to have boiling point elevation, so things will boil at a higher temperature. Freezing point depression, things will freeze at a lower temperature. That's why they put salt on the roads, because when they put the salt on the roads, it freezes at a lower temperature. Normally, the roads will freeze, I'm going to do Fahrenheit here, at 32 degrees Fahrenheit. If you put salt on the roads, then that salt water will freeze at a lower temperature, let's say 25 degrees Fahrenheit. I don't know the exact number. Okay. And that's why in the winter, sometimes people will say, well, they can put salt on the roads, but it won't do any good. It's too cold. Have you ever heard them say stuff like that? Well, people will. Okay. And it's true, because after you get to a certain point, that salt is not going to affect it anymore, and it's still going to stay frozen. Okay. They put the salt on the roads to get it to that slushy so that you still have more traction. Because on the ice, you're just gone. All right. And then osmotic pressure, which we'll get to at the very end. Okay, so freezing point depression. How does this work? This is going to be our equation that we're going to use for this. Okay, and what this equation does is it's going to give you the interference factor. Okay, that we talked about earlier. This KF value, they have to give you that in a chart. You won't need to know that off the top of your head. It will be given to you in a chart. And then molality. So we talked about molality earlier. So molality equals moles of solute over kilograms of solvent. Okay. So here is our problem that we're given. Okay, at what temperature will water freeze if we have 100 grams of glucose dissolved in 500 grams of water? So we are going to figure out our interference factor. This is a molecular solid. So what's the interference factor for any of the moleculars? 1. Okay, because it's not going to break apart. Right? So my change in temperature is going to equal 1 for that interference factor. My KF, well, we're trying to freeze water. So we're going to go over to our table here, and we're going to find our KF value off of that. So that is 1.86. Then I'm going to multiply that by my molality. So my molality here for this guy, my molality is going to equal 100 divided by 180. That's going to get me into moles. So that's 0.56 over kilograms of water. So I've got to convert that into kilograms, and you guys should be getting comfortable with converting into kilograms. So my molality here is going to equal 1.11. Right.
I'm confused where you're getting a lot of these numbers.
Okay. Which number?
1.86.
Okay, 1.86 came from right here in the chart.
What about... Actually, all the numbers. I don't know where you're getting anything
Okay.
from.
So the first number here is the interference factor. Okay, we talked about that earlier. We said if we had something that's a molecule, it's not going to come apart. So its interference factor is going to be 1. This is water. So I'm going to come over to the chart here, and I'm going to get the KF value for water. So that's where I got the 1.86. The molality then is little m. I need to have moles of solute. So moles of solute is going to be 100 divided by 180 because that's the molar mass of glucose. So that gave me 0.56. And that's divided by kilograms of the solvent. So I took 500 and divided by 1,000. And that gave me 0.5. Right. So I'm going to divide those, and that's going to give me my molality. So then I'm going to bring that up into my equation here. Times 1.86, and I end up with a delta T. So my delta T is going to equal 2.07 degrees Celsius. Now, what does this delta mean? When you see a delta like this, what does that mean? Do you guys know what that means? It means change in. Okay. So this delta means that our temperature means change in the delta. Okay. And you'll see that all over science. So get used to it. That means that the temperature is going to change by that many degrees. Now, this is freezing point depression. So that means that my freezing point is going to go down. My freezing point normally is 0. So what is my freezing point going to be now? Negative 2.07 degrees Celsius. That is my answer. I have to take what my freezing point would normally be and subtract that temperature from it. Good? What's wrong, Ray?
I'm confused, Jim.
About what?
Where did we get 2.07?
I multiplied 1 times 1.86 times 1.11.
Oh, I have to write that down.
So I know that you used 100 grams and you divided that by 180 to get the moles of glucose. What did you use the 500 grams?
Right here. I converted it into kilograms.
Okay.
Because remember, this has to be kilograms of solvent.
Okay.
For molality. Molality is the one where you don't have a total on the bottom. Because normally, like, it's usually part of or whole for all of these. But this is the one where you don't. It's a part of or a part.
Okay.
All right, let's try one where it's not a molecular solid. Okay. So here, we're trying to figure out what temperature the water is going to freeze at. We have 100 grams of sodium chloride, and that's in 500 grams of water. So step 1, I am going to take this sodium chloride. I'm going to divide by its molar mass, and I'm going to get moles of sodium chloride. So 100 divided by 58.5 is 1.71. And that is my moles of sodium chloride. I'm going to divide that by kilograms of water, which would end up being 0.50 or 0.500. And that gives me a molality of 3.42. That's little m. So that's my molality. Now I'm going to plunk that into this calculation here. So delta T equals my interference factor, my Kf, and my molality. This is sodium chloride. It is an ionic compound. How many parts is this going to break up into? 2. So I call that my interference factor. Okay, so that's going to be 2. My Kf value, I'm going to again come over to this chart. I'm going to find water, and I'm going to grab my Kf value and bring it in to this problem. My molality, we calculated up here. I'm going to bring that down into this problem. And I'm going to calculate my delta T. So that ends up being 12.7, I guess it would be 2 if we rounded. All right. So that's how much my temperature is going to change. This is freezing point depression. So we're going to take what the freezing point normally would be, and we are going to subtract that amount from it. So 0 minus 12.72 is a negative 12.72 degrees Celsius. And that is my final answer. That's why salt is effective on the roads, because it's going to drop that temperature down. They're not going to use that much salt on it, though, so it's not going to drop it that much, but you get the idea, right? All right. Any questions on freezing point depression? We also have vapor pressure lowering. So again, these particles are going to interfere with that material becoming a vapor. So less of that stuff will become a vapor, less pressure on the container. So it's going to lower that vapor pressure. We also have boiling point elevation. So here it's going to increase the boiling point. Okay. Math is done in a similar fashion. So you are going to take your substance here, and we are going to just plunk stuff in. So here, our change in temperature is going to equal, we're dealing with calcium chloride. This is a metal and a non-metal ionic bonding. How many pieces is this going to break into? 3. So our interference factor is going to be 3 here, because I'm going to get 1 calcium and I'm going to get 2 chlorines for a total of 3. My Kb value, I'm going to find my substance. This is aqueous. So what substance is that? Going to the aquatic center, what are you going to do? Water, exactly. So this is aqueous, so it's going to be water. So we're going to pick that out of here. So my Kb value is 0.512. And my molality, they already have this calculated for us. So we don't have to calculate molality this time. We're just going to grab that value and plunk it in. So I get a delta T value of 2.304. That's degrees Celsius. Now, this is boiling point elevation. So now, instead of subtracting, we are going to add. So I'm going to find my boiling point in my chart up here for the substance I'm dealing with, and I'm going to add this amount to it. So my new boiling point, which is what they asked us for, is going to be 102. Okay. And then osmotic pressure is just another one. Don't get wigged out about that. It's not going to be on the test or anything. If you get into AP Bio, they may talk about osmotic pressure in there, but so that's the only reason I bring it up. That's it. You are done with chapter 14. Give yourself a